Thank you, thank you, thank you. Hope you're feeling a bit more refreshed and energized after a fix of coffee. It's a tough slot to be talking late in the day, but I think you're going to be a bit more energized after you see this demo, because who doesn't love seeing some flashing LEDs? My name is Vella. I'm a solutions engineer at Confluent, and if you're not familiar with Confluent, Confluent is a data streaming platform that was built by the founders of Apache Kafka. And working at Confluent in this region has really given me the opportunity to see many customers and many interesting use cases solving some really unique challenges. So over the next about 20 minutes or so, we're going to take a look at a bit of an interesting application of a data streaming pipeline of real-time edge processing that is being used to solve, I think, a pretty interesting problem. So the challenge was set. How do we prevent equipment failure and provide real-time analytics on a ship that's sailing in the middle of the ocean without any connectivity to the internet? And of course, when a challenge like this arises, there's no better opportunity to use that as an excuse to play around with a 3D printer and a Raspberry Pi. So I set off and I said, I'm going to build this little demo to see how we can actually simulate this using a technique around processing event streams in real time on an edge device. So the first question I asked myself was, how can we actually do this using event streaming patterns? So Raspberry Pi in Confluent is just a match made in heaven. And of course, there's some key event streaming capabilities here that we can use, starting off with Apache Kafka. Now, Apache Kafka is a storage layer used to support publishing and subscription of data streams. And it's not just about moving events around through like a queue. Kafka is actually a storage layer. So you can kind of think of Apache Kafka in this scenario as kind of like a flight recorder for the IoT data that's being generated on the actual device itself. But then we need a bit of a layer to process this data. So using stream processing, we can use ksqlDB as a stream processing layer to do some really interesting processing on the actual device. So we can do things like filtering out data streams, masking data, joining data from multiple streams together to create some interesting data sets. And we'll look at how we're using ksqlDB to generate some reactions on this device itself. Of course, we need a way to specify and introduce some data quality into the streams of our data. And using a Schema Registry, we can use things like Avro and JSON schemas to really ensure that our data streams are of a certain quality and that we can describe the events that are actually flowing through the streams themselves. But we need to get the data off the ship somehow, right? So using cluster linking, we can take a certain set of data streams off the actual device and send that into cloud, in this case, for further upstream processing. And that could be for analytics purposes, as we'll see in the demo. And then lastly, using pre-built connectors, we want to send this data and do some interesting things with this data that we're generating. So using the Confluent pre-built connectors, we want to connect this into some dashboarding tool to actually see this data in a live dashboard. And all of this is running on a Raspberry Pi on the device, and we'll see how we're sending that up into the cloud. So here we have a very highly technical drawing of the ship. And we're just going to talk through the kind of concept and the architecture of the demo, and then we're actually going to dive a little bit deeper into how it's actually running. So the idea is that on the Raspberry Pi, which is located on the actual ship itself, we're running the core components that we need. So we're running Apache Kafka, we're running ksqlDB, and we're running an instance of the Schema Registry. The core components that we need to be able to process these event streams. We take data from a temperature probe, which is this little guy that's sticking out the top here, that's recording the current temperature in this room as we speak every 1 second to a topic within Kafka. And that data is just being logged every second, the current temperature. We've also got some other probes on the ship. They're just simple Python microservices that are doing things like testing internet connectivity, testing the health of the Confluent platform, and just testing out the temperature so we can turn on and off these lights. But this temperature probe is just logging the data on the ship. And the idea here is that we take this raw data, which is just a stream of temperature readings, and we do some processing on the ship for things like, is there a spike in temperature in the last minute or so? And let's react to that event, right? And so we've got a ksqlDB application that's running in real time that's measuring a change in temperature, and if there is a change, generate another event. And we have another service that's just listening for those warning events that will trigger off a sequence of lights here, which is just simulating a warning signal like something's gone wrong. And we've also got other sensors as well that's just checking for internet connectivity, and if the health of the Confluent platform is not running, it'll change the color of the LED lights. So you can kind of think of this demo as doing on-ship raw data aggregation, but also event-driven reactions where the LEDs are actually reacting to events that are happening on the ship. And we take this data and we use cluster linking to send it, in this case, to Confluent Cloud. Now in Confluent Cloud, we're running another instance of the Confluent platform, which is effectively, in this case, Kafka, ksqlDB, and the Schema Registry. And we're receiving only a copy of the aggregated data set. Because of course we don't need to see every reading every second. So we only want to send an aggregated copy of the data because in this case here, our internet connectivity is quite unstable. And once the data is in Confluent Cloud, we're then using a Splunk connector to send that data set into a Splunk dashboard, just as an example to showcase how we can use that data in a dashboard. So let's actually see how that's running. So we can just get this video played. Okay, so here I'm just going to log into the Raspberry Pi and just check that the Confluent services are up and running. So this is just Confluent services running natively on the Raspberry Pi. They can also be run in a Docker container on the device itself, but in this case it's just running natively on the Raspberry Pi. Here we can see that they're active, they're running, they're ready to receive some data. Next, I'm going to check the Python services. So in this case here, I just want to check that my Python services are running, and these services are just literally producing data to Kafka and consuming data from Kafka. That's all they're doing. We'll look at a producer application. So this is a Python application. It's very kind of standard way of writing a producer bit of code. But just to show you the actual line of code that's going to connect into Kafka first. So we just create a configuration into Kafka. And it's a serializing producer, which means that we're going to serialize it in Avro. We're going to get the temperature from the actual sensor, and we're going to literally just produce an event into a Kafka topic. And this will just happen every second on a loop. And now we'll see what that data looks like on Kafka. So here I've got the control center, which is just a control plane as a view into the ship itself. And here we can see the Kafka topics that are running on the Raspberry Pi. There's a few topics here, there's not that many of them. But the first one that we'll take a look at is the actual raw IoT temperature data. This is just a topic that's storing events as they're happening in real time. As we can see here, every second we get an event that's coming from the current temperature. We can actually look at the schema of the event as well. This is a function of the Schema Registry. This is a description of the event. It's a very simple event, and it contains the source where it came from, the temperature reading itself, and a timestamp of when that temperature was read. And this is again a way that we can describe the event so that we can ensure that the events meet a certain quality. Here we can see some more topics of the other data sets that are coming into Kafka. But we want to do some processing with this data. So using ksqlDB, which is currently also running on the ship itself, let's take a look at the flow of data in a stream processing pipeline. This is the ksqlDB interface. Here we can see the streams that are available to look at. And we'll take a look at one specific flow, which is the temperature streaming flow. So starting off with that raw data, which is what we just saw before, here we can see the raw data events being produced into ksqlDB stream. Now, ksqlDB also has the concept of a table, which if you're familiar with the database, is a way that you can actually query your data in Kafka, but in tabular form, right? And let's take a look at what we can use that for. So in this case here, we don't want to look at all of the events that happened, every single second. We want to use ksqlDB to materialize a view of the data and just give us the latest temperature. So here I'm back on the Raspberry Pi, and I'm using the ksql command line interface to write a very simple select statement to view the last temperature. You'll be very familiar with this language. ksqlDB is a SQL-like language to query data in Kafka. These are the tables that I've created in ksqlDB, and I'm literally just going to do a select all from a table called latest temperature, and here I can see the latest temperature. And the thing to note about this is a table view giving me just the last event, okay? And we'll see here as the temperature changes, the query will now start showing us that latest event, that latest changed temperature. So you can kind of use Kafka to materialize data into a view and actually query it like you're querying like a relational database, right? That's pretty cool. But we can do some other interesting things with the data as well. So the first thing we want to do here is actually compare the current temperature with the temperature that was last read. So I'm just taking the current temperature and the temperature reading that was one before, and I'm just creating another event stream from that. And so in this event stream here, we'll see that this new event just gives me where in the topic my current reading is and the previous one. And this is how we'll find those events to calculate the percentage difference between those two readings. So further on in the pipeline, we're creating another stream here, which is going to calculate the percentage difference between the current temperature reading and my previous reading. That's all it does, okay? It's a very simple create stream statement, very similar to SQL language. If you're familiar with using SQL inner joins, you'll be very familiar with this. But here we get a really interesting data stream because now we get the percentage difference between the two temperature readings. We'll take a look at an example of this. Our current reading is 22, and the previous reading here was 21.9, so the percentage difference is 0.2%. This is all calculated on the fly every time an event stream has been processed. There's no back-end databases for this. It's just all running through a stream processing pipeline. And with this data, we can materialize this into some other interesting views. So here I'm creating another table. And we want to do things like, what's the maximum temperature? What was the average temperature, minimum temperatures, and what was the maximum change in temperature? And I'm taking a view in 30-second windows, okay? So if we go back into ksqlDB and we look at this next table, this temperature stats table, we can actually start to do some real-time aggregation and calculation on that data set and look at things like mins and max in 30-second windows, okay? So you can use stream processing to slice up your data, join data from other data streams, and do actual processing and calculate some statistics on that data as it's flowing in real time. We've got some window start and ends here, how many readings there was, the max temp, min temp, average, and the change in percentage. All of this data is stored in a Kafka topic. There's no other databases here. The next way we want to look at this data is we actually want to generate a warning event when the percentage change between the previous and the current value is above a certain threshold. And this event here will only be generated when that warning event happens. Okay, so if we take a look at this actual stream itself, I think I've got the threshold set to 0.4%, just so we can actually see it changing. So if the percentage difference is 0.4%, create a new event, okay? Now that consuming application is just listening and waiting for every time one of these events happens, and when it receives one of these events, it'll then trigger the sequence of red LED lights that you might have seen spinning. This is just, again, another way to see stream processing in a decoupled fashion between producer and consumer. And of course, we can create some other materialized views. In this case here, we're just taking an average of those temperature changes in 1 minute intervals. And we're going to use this particular topic as the actual topic to send the data to our cloud environment, which we'll see shortly here. So this table here is just what was the temperature, or was the average temperature of all of those readings in 1 minute intervals. And as I keep refreshing this query, we'll see the number of readings there increase as new readings are being generated from our real-time stream of raw events. And we can see them increasing there. And that's our current average temperature. So we want to take that value, and that can be the value that we want to send into Confluent Cloud because we don't need all the raw data streams. And then the final thing that we do in this particular pipeline is we just want to convert the data from Avro, which is what it was into JSON for our upstream consumers. So in this case here, with this one-line command, we're just converting it from an Avro format into a JSON format. And we can do the same thing if we want to convert it into protobuf or back into Avro as well. Again, this is our final data stream of every event, every warning event that happened, but now it's in JSON format. So we have the two streams now that we want to send to the cloud. Every warning event and only the temperature, the average temperature over 1 minute intervals. So what you're looking at here is now Confluent Cloud, a SaaS platform. It's a dedicated cluster, in this case running in AWS. And this cluster is a fully managed cluster. We can see some data coming in here. And we'll take a look at cluster linking and how you can use cluster linking to link data sets between two different clusters. So here are the two topics that you see in Confluent Cloud. They are the aggregated data set and the temperature warning stream here. Only two of these topics are being replicated to Confluent Cloud. We can see that mirroring is active. I've got a cluster link created called from_ship_link, and we can see the messages start flowing through here. In this case here, this stream will only receive events every minute because it's averaging all of the temperature readings. So here we can see what the average temperature was in 1 minute intervals, which is a great use case because we don't want to see all the raw IoT data. In that case, there was 72 readings in that particular interval. Let's take a look at the cluster link itself. So this cluster link has been set up to pull data basically from the cluster or the instance that's running on my ship on the Raspberry Pi and only send these two mirror topics into a cluster in AWS. You can easily replicate this between multi-cloud environments, and you can chain these clusters as well if you have more than one cluster that you want to copy data to. And now that the data is in the cloud, we can use a connector. In this case here, I'm using two instances of the Splunk sync connector, so taking data from Kafka and syncing it into Splunk so that we can create some nice dashboards around this. We've got lots of connectors available for pretty popular sync systems. So here we can see the configuration that's required for a sync connector. So we supply the topic names, the credentials to Kafka, credentials into the Splunk HEC receiver as well. It's JSON format, some very basic, this is all basic standard configuration out of the box that you get through the connector, and then the connector is launched, and it will just listen onto every event that's happening. And then using those same events, we can then create visualizations, right? And so the whole idea here is that this dashboard would be running on the shore, and it's only receiving aggregated events that are coming from the ship, and in this case here, it's an average reading every minute. And so we're not wasting bandwidth and sending the raw data, which is stored on the ship. We're getting the aggregated data that's running, that's sent into the cloud. And in that case, we're basically saving the bandwidth, but when the internet connectivity is unavailable, that data will just bank up in the Kafka topic on the ship for when the internet connectivity is available again. That could be for hours, we can store that data on the Kafka topic indefinitely. So that data is in Confluent Cloud, it's in Splunk, and we can now do whatever we want to do with that from a visualization perspective. So that's the demo. If you're interested in setting up something similar to this, we've got some pretty cool ksqlDB recipes on the developer.confluent.io website. And you can sign up to Confluent Cloud as well. And we've got some vouchers on our table as well. Come down to our booth if you want to have a look at this in a bit more detail. But yeah, head over to developer.confluent.io and hopefully you enjoyed that. Thank you.